Good morning, students. Uh, Today our topic is radiations from an oscillating dipole. Radiations from an oscillating dipole. Um, for this, let us consider two small spheres lies on the two ends on the small wire. This is the wire along the z-axis, and its two ends have two small spheres. Now let charge is transferred from one sphere to another periodically. Periodically, that means charge transferred uh, after a definite interval of time. So Q is equals to Q naught e power iota omega t, and here Q naught is amplitude of oscillating charge and omega is angular frequency of oscillation. So charge will transferred from one sphere to another sphere periodically according to the equation first. Now if we assume that the wavelength of the radiation produced is very large in comparison to the length of the wire, that means lambda is greater than small l, length of the wire, then lambda is equals to 2 pi c divided by omega will be greater than l. So t is equals to 2 pi upon omega is greater than l upon c, or t is greater than l upon c. And if we differentiate the equation first with respect to time t, then we get I is equals to dq by dt is equals to iota omega q naught e power iota omega t, iota omega q naught e power iota omega t. An oscillating charge between two spheres is similar to the oscillating dipole, whose dipole moment is given by P is equals to Q into L. That means charge into length of the dipole. So P is equals to Q into L, and this will be equal to Q naught L e power iota omega t. And if we put Q naught L is equals to P naught, then we get P is equals to P naught e power iota omega t. And we can write it in terms of current, P is equals to IL upon iota omega. Now wire is along the z axis, so we have to find the field at point P whose position vector is R. We have to find the field at point P whose position vector is R, and this is the diagram, and we have to find the field at point P whose position vector is R. This is the point P and its position vector is R. Now A is equals to mu naught upon 4 pi volume integral j r dash t minus modulus of r minus r dash divided by c d tau divided by modulus of r minus r dash. Now we can write that current density j r dash t minus r minus r dash divided by c, j r dash t minus modulus of r minus r dash divided by c d tau is equals to I r dash t minus modulus of r minus r dash divided by c e cap dz. Since current is always along z axis, so we can replace r dash by z. Current is always along the z axis, so we can replace r dash by z. Now in terms of the z, we can write field vector potential A is equals to mu naught upon 4 pi minus L to integration from minus L by 2 to plus L by 2. I z t minus modulus of r minus e z cap z divided by c e z cap dz divided by modulus of r minus e z cap z, and e z cap is unit vector along z axis. And now if since r is greater than L, so e z cap z can be neglected in comparison to r. So we can write the vector potential A is equals to mu naught upon 4 pi integral from minus L by 2 to plus L by 2, and I z t minus r by c e z cap dz divided by r. Now vector potential A is equals to mu naught upon 4 pi e z cap L I t minus r by c divided by r. So it is clear from the above equation that vector potential A is parallel to L at all points. It is clear from this equation that A is along the z axis, because on the right hand side the unit vector is along the z direction. Now, so in this case Ax r t is equals to 0 and Ay r t is equals to 0. Now if we put this value, if we put value of I t minus r by c from equation 2, then we can write equation 2 is this. If we put the value of I t minus r by c from equation 2, then we get Az r t is equals to mu naught upon 4 pi L by r iota omega q naught e power I t minus r by c omega. And if we put q naught L is equals to p naught, then we can write Az rt is equals to mu naught upon 4 pi p naught r iota omega e power iota omega t e power minus iota omega r by c, and equation becomes Az rt is equals to mu naught upon 4 pi r p iota omega e power minus iota omega r by c, and Az is equals to mu naught upon 4 pi iota omega divided by r pt e power minus iota kr. Az is equals to mu naught upon 4 pi iota omega divided by r pt e power minus iota kr, and pt is equals to p naught e power iota omega t. And if we write the equation in terms of differentiation of the p with respect to time t, then we can write Az is equals to mu naught upon 4 pi r p dot t e power minus iota kr. If we arrange the equation, then we can write Az is equals to mu naught upon 4 pi p dot t e power minus iota kr divided by r. Now we know the Lorentz condition. Lorentz condition is del dot A is equals to minus 1 by c square del phi by del t, and only z component of A is non-zero. So in this case we can write del Az by del z is equals to minus 1 by c square del phi by del t. If we write del Az by del z is equals to del Az by del r dot del r by del z, so we can write del Az by del z is equals to del Az by del r cos theta, since del r by del z is equal to cos theta. So put this value in the above equation, then we get minus 1 by c square del phi by del t is equals to mu naught upon 4 pi p dot del by del r e power minus iota k r divided by r cos theta, and del phi by del t will be equal to minus c square mu naught upon 4 pi p dot del by del r e power minus iota k r divided by r cos theta. And if we put c square in terms of mu naught epsilon naught, then we can write del phi by del t is equals to minus 1 upon 4 pi epsilon naught p dot del by del r e power minus iota k r divided by r cos theta. And on integration on both the sides, we can write phi is equals to minus 1 upon 4 pi epsilon naught pt cos theta del by del r e power minus iota k r divided by r. And we can find E and B after finding A and phi. And so in polar coordinates, vector potential components can be written as AR is equals to mu naught upon 4 pi r iota omega p naught cos theta e power iota omega t minus r by c. AR is equals to mu naught upon 4 pi r iota omega p naught cos theta e power iota omega into t minus r by c, and AR will be equal to mu naught upon 4 pi r p dot cos theta e power minus iota k r, and A theta will be equal to mu naught upon 4 pi p dot sin theta e power minus iota k r, and finally A phi is equals to 0. And components of E and H are as follows: ER, E theta and E phi is equals to 0. Components of electric field ER is equals to iota p k cos theta divided by 2 pi epsilon naught r into 1 minus iota upon k r e power minus iota k r divided by r. Similarly, E theta is equals to minus p k square sin theta divided by 4 pi epsilon naught into 1 minus iota upon k r into 1 minus iota upon k r into e power minus iota k r divided by r. E phi is equals to 0 and HR is equal to 0, S theta is equal to 0, H phi is equals to minus c p k square divided by 4 pi sin theta into 1 minus iota upon k r and into e power minus iota k r divided by r. H phi is equal to minus c p k square divided by 4 pi sin theta into 1 minus iota upon k r into e power minus iota k r divided by r. And these equations 7 and 8 are known as Hertz relation for oscillating dipole. Equations 7 and 8 are known as Hertz relation for oscillating dipole.